Good morning, Alex. Welcome, and thank you for joining us for the AI and Machine Learning Engineer position. Hi, Mavis, David. It's good to have you all here. I'm Jeannie, and I'll be chairing today's interview. We'll begin with brief introductions from the panel, and then we'll come to you. Let's start with Mavis.
Hello, Alex. I'm Mavis Brown from Human Resources. I'll be focusing on your overall fit, communication, and experience.
Greetings, Alex. I'm David Wilson, the subject matter expert for this role, particularly in AI and machine learning engineering. I'll be discussing the technical aspects with you.
Thank you, panel. Alex Morgan, you may proceed with your introduction. Kindly outline your background, professional experience, and your interest in the AI and machine learning engineer role.
Good morning, everyone. It's great to be here. My name is Alex Morgan. I'm an AI and machine learning engineer focused on building production AI systems, not just prototypes. Most recently at NeuroWorks, I led work on deploying machine learning pipelines with Fast API, Docker, and Kubernetes, focusing on reliability and low latency inference. Before that, I built NLP document understanding systems and recommendation engines, developing full pipelines from data prep to model deployment. I'm interested in this role because it goes beyond simple API integration. It involves agentic systems, enterprise search, and probably voice or document AI at scale, which is the kind of hard, meaningful engineering I enjoy.
You mentioned leading work on deploying ML pipelines with Fast API, Docker, and Kubernetes at NeuroWorks. Can you walk us through how you specifically optimized for low latency inference in that environment?
Checking that. Absolutely. In one of the production systems, the goal wasn't just to make the model faster. It was about hitting a latency target without sacrificing quality. First, we profiled the inference pipeline carefully. Instead of guessing, we measured where time was actually spent. Pre-processing, embedding lookup, model inference, and post-processing. We ran Fast API with async endpoints, containerized with Docker, and deployed on Kubernetes using stateless pods for horizontal scaling. On the model side, we tuned batch sizes and profiled GPU utilization, keeping models preloaded to avoid cold starts. For retrieval, optimizing chunk size and using cached embeddings in Redis made a big difference. And on the infrastructure side, we used Kubernetes horizontal pod autoscaling plus rolling deployments with health probes, so updates didn't interrupt live traffic. Then we continuously monitored P95 latency, request throughput, and cache hit rates in Grafana. If latency trended upward, we checked metrics first, rather than immediately changing the model. Honestly, the big lesson was optimize the whole serving pipeline, not just the model. Measuring, making targeted changes, then validating consistently worked better than focusing on inference alone.
Can you describe a specific production-grade AI system you designed and deployed, focusing on the challenges you faced with scalability or latency?
Checking that. Certainly. One system I'm proud of was an enterprise RAG assistant. We built a document ingestion pipeline, a Fast API backend for retrieval and prompt assembly. The challenge was scalability. As usage grew, retrieval latency started to climb. We profiled each stage, optimized chunking, added Redis caching for frequent queries, and deployed with Docker on Kubernetes using stateless services and async request handling. We kept a close eye on P95 latency, cache hit rates, and GPU utilization in Grafana. The real lesson, it's not just the model. It's the entire pipeline that determines user experience.
How did you specifically optimize the Fast API backend or vector store to handle increased query volume without degrading response times?
Checking that. Good question. We handled it on two fronts. On the Fast API side, we used async endpoints to handle concurrent requests efficiently, keeping services stateless so Kubernetes could scale them horizontally during traffic spikes. On the retrieval side, we tuned chunking, limited context size sent to the LLM, and cached frequent query results in Redis. As load increased, we profiled before changing anything, and in one case found retrieval was the dominant contributor to latency, not the model. So instead of touching the model, we optimized indexing strategy and caching. That kept latency low even as the number of users and documents grew. It really came down to measuring first, then scaling smart.
You mentioned optimizing chunking strategies. Which specific text splitting algorithm or overlap settings did you find most effective for your document types, and why?
Checking that. For our mix of technical docs and knowledge bases, I found recursive character-based splitting worked best, starting with around 500 to 800 token chunks with 10 to 20% overlap. We tuned empirically, balancing retrieval precision against latency and cost, rather than relying on one fixed algorithm.
How did you handle the trade-off between chunk size and context window limits when deploying this solution on different LLM providers?
Checking that. That was an important design consideration. We kept chunking mostly provider agnostic and adjusted retrieval, not indexing. For models with larger context windows, we didn't just stuff in more text. We prioritized retrieval quality. More text often just increased latency and cost without better answers. We monitored token usage and latency per provider. If a provider had higher latency, we reduced retrieved chunks or added a re-ranking step to keep prompts concise. So, rather than building separate indexing pipelines, we decoupled indexing from inference, so we could swap or compare LLMs easily without rebuilding the whole index. Ultimately, those choices were data-driven, picking the balance that gave the best retrieval accuracy and response times for each provider.
When you say prioritized, did you implement a specific re-ranking strategy or query transformation to maintain precision without exceeding the token budget?
Checking that. Yes, we used a retrieval pipeline, re-ranking the top retrieved chunks, and for complex queries, transforming the query by expanding keywords or clarifying intent before retrieval. We kept the token budget by only including the highest ranked chunks that fit. Every added step had to justify itself. If re-ranking improved grounding but added too much latency, we simplified. Decisions were always driven by measured performance, not assumptions.
What specific metrics did you track to determine when the added complexity of re-ranking or query transformation was no longer justified?
Checking that. Good question. We tracked P95 latency, retrieval precision at K, answer grounding quality, and token consumption. If re-ranking added latency without a measurable lift in grounded accuracy, we simplified. We also watched user outcomes, task success, feedback, and rephrase rates. If no meaningful gain showed up, the added complexity wasn't worth its overhead. I basically believe every component in a production pipeline has to earn its place with measurable improvements. Otherwise, simpler is better.
Which of those metrics, P95 latency, precision at K, or grounding quality, did you find had the strongest correlation to user satisfaction in your production environment?
Checking that. In my experience, grounding quality correlated most with user satisfaction. People will tolerate a few hundred extra milliseconds, but wrong answers or hallucinations quickly erode trust. That said, I still balance it against P95 latency and precision at K. But if forced to pick, grounding quality comes first. The best user experience, in the end, comes from correct grounded answers consistently, even if they're a touch slower.
How do you handle cases where high grounding accuracy requires significantly more tokens, pushing against your budget constraints?
Checking that. That's a common trade-off. I first optimize retrieval quality, sending only the top few most relevant chunks. Then trim redundant text inside chunks and keep token budgets dynamic, allowing more tokens only for complex queries where they tangibly improve grounding. We constantly measured token consumption, P95 latency, and grounded answer quality. If increasing context only slightly improved accuracy, but spiked cost and latency, we'd roll it back. The principle is simple. Tokens are a resource to optimize, not maximize. The aim is grounded accuracy within our latency and cost targets.
When you trim redundant text inside chunks, what specific heuristics or metrics do you use to decide which content to drop without hurting grounding quality?
Checking that. Great question. I don't use simple rules like cut after end sentences. Instead, we prioritize semantic relevance after retrieval, remove duplicate info across chunks, and preserve semantic boundaries like never cutting a procedure mid-step. Metrics like grounded answer quality, citation accuracy, token usage, and P95 latency tell us if we're cutting too aggressively. The rule of thumb: every token should contribute evidence to the answer. If not, it's a candidate for removal. But we always verify with data.
Which specific metrics do you track in your CI/CD pipeline to automatically flag when retrieval quality drops below acceptable thresholds?
Checking. In a production setup, I'd have CI evaluate retrieval and answer metrics like precision at K, MRR, and DCG, grounded answer quality, citation accuracy, and hallucination rate. If they fall below thresholds against a fixed regression set, the pipeline failed the build. We also track P95 latency and token usage per request. The idea is to treat AI evaluation like software testing. Every model update or retrieval tweak has to pass automated checks before it reaches production. That keeps us confident we're actually improving the system.
What specific regression test cases do you include in your fixed set to catch subtle degradation in retrieval quality?
Checking that. We include real user-like queries, straightforward factual retrieval, multi-document reasoning, ambiguous queries, long document lookups, and edge cases from production. We also add negative cases where the answer doesn't exist, ensuring the system says, "I don't know," instead of hallucinating. And we track grounded citations, P95 latency, and top K accuracy against a fixed baseline. Plus, every production incident or failed eval becomes a permanent regression test. Over time, that suite grows more representative and catches subtle regressions before users ever see them.
How do you handle the trade-off between increasing your fixed regression set size to catch edge cases versus maintaining low P95 latency and token usage in production?
Checking that. Great question. I actually separate the regression suite from production. It runs in CI/CD, not live requests. So test suite size doesn't affect P95 latency in production. Instead, we balance depth and practicality. Fast smoke tests per pull request, full regression pre-release, and canary deployments for final validation. If the suite gets too large, we consolidate redundant cases. But every real production incident earns a spot. That way we maintain high confidence in retrieval quality without impacting latency or cost for users. Good morning. It's 10:06 right now. Ready when you are.
Since you're fluent in German, how do you handle a situation where your technical team needs to align on an AI project strategy, but there's some disagreement between the English-speaking and German-speaking members?
First, I'd make sure everyone's actually heard. Sometimes the disagreement's just phrasing. So I'd restate each concern neutrally, confirm understanding, and maybe do a short recap in simple English and simple German, if helpful. Then I'd steer the team towards shared criteria like success metrics or user impact rather than language nuance. Once the goals are unified, the team usually converges naturally.
That's a solid approach to de-escalating tension. Given your experience with scalable backend services and CI/CD, how would you apply that same structured mindset if the disagreement wasn't about language, but actually involved conflicting technical decisions on model architecture or deployment strategy?
I'd still slow things down a bit first. Get clarity on the actual goals. Like, are we optimizing for latency, accuracy, cost, or deployment simplicity? Then I'd map each proposed approach against those metrics. Like, if one architecture wins on scalability but adds too much operational complexity, I'd suggest maybe prototyping both in a small environment, measure actual performance and operational burden. My default is not to win the argument, but to design a quick experiment that gives us data to decide.
That experimental mindset fits well with an engineering-first approach. If you ran that prototype and the results were inconclusive or showed no clear winner, how would you handle pushing for a decision without letting the team stall indefinitely?
When tests don't give a clear answer, I'd set a decision deadline upfront, agreed with stakeholders. If results are statistically flat, I'd consider other factors: team expertise, maintainability, long-term operability, and I'd push for a call rather than endless analysis. Sometimes good enough with mitigation beats perfect clarity that never arrives. So I'd recommend documenting assumptions, picking one path, and monitoring it closely. And commit to revisiting if new data or production metrics suggest otherwise. That prevents paralysis while still staying evidence-driven.
That's a pragmatic way to avoid analysis paralysis. Since you're also experienced with fine-tuning LLMs and voice AI, can you share a specific time when you had to pivot your technical strategy mid-project because user feedback or production metrics showed the initial model approach wasn't meeting business needs?
Checking for a good one. Yeah, I want to be careful here. My strongest production experience has been with RAG systems and deploying machine learning models, rather than fine-tuning foundation LLMs or end-to-end voice AI. One example, we were building a RAG assistant for an enterprise knowledge base. Initial version focused on high recall, but production metrics showed latency creeping up and user feedback saying the answers were too verbose. So instead of retraining the model, we adjusted chunking, reduced retrieved documents, added re-ranking, and improved caching for hot queries. We monitored P95 latency and grounded answer quality. That mix gave us faster responses without compromising accuracy. Personally, it reminded me not to jump straight to model changes. Measure first, fix the system bottlenecks, then consider retraining.
That focus on measuring P95 latency and grounded answer quality before changing models is a great example of an engineering-first mindset. Given your background in Kubernetes and containerization, how do you typically structure the CI/CD pipeline to ensure that these production metrics are automatically validated during deployment rather than just relying on manual checks?
Checking. My goal is to bake those gates into the pipeline. So every commit runs lint tests, unit tests, and retrieval evaluation against a fixed regression dataset. If those pass, the pipeline spins up a test environment, runs load tests to capture P95 latency, and then deploys using canary releases in Kubernetes. Dashboards in Prometheus and Grafana track latency, retrieval times, token usage, and error rates. If metrics breach thresholds, the pipeline automatically halts rollout or rolls back. Treat model deployments like any critical software release. Don't push to prod until the numbers say it's safe.
That automated rollback strategy for latency breaches is exactly what we need in production. Since you mentioned working with enterprise knowledge bases, can you describe a specific conflict where stakeholder expectations clashed with these technical constraints? How did you navigate that conversation to align the team on realistic delivery timelines without compromising quality?
Checking the record. One example was during the rollout of an enterprise RAG assistant. Stakeholders wanted to expand the knowledge base fast. Metrics showed rising retrieval latency, so I framed the trade-offs clearly, with data, not opinions. Instead of saying no, I proposed a phased plan. Optimize retrieval pipeline, onboard high-priority docs first, and measure in production before scaling. We agreed on success criteria: latency targets, grounded answer quality, and user adoption. That kept the relationship constructive, and everyone knew what ready actually meant.
That phased approach to aligning stakeholder expectations with technical reality is exactly how we want to see you handle pressure. If a new project came in tomorrow requiring rapid deployment of an AI agent, but your team identified significant risks that would delay the timeline, what specific steps would you take to communicate those constraints and propose a viable alternative without losing trust?
Checking. I'd start by being honest, data-driven, and solution-oriented. I wouldn't just say no. Instead, I'd outline the risks in plain language, show how they might impact business outcomes, and then propose a phased delivery plan. For example, deliver a minimum viable scoped agent, start a pilot or canary release, gather production feedback, and expand in stages. I'd set clear milestones and success metrics so stakeholders know what's getting delivered and when. Throughout, I'd communicate openly and keep the focus on measurable outcomes, not technical jargon. That way, trust stays intact, and we still move quickly without sacrificing quality.